Hi class, welcome to section 2.2. Today we're going to talk about graphs of functions. We talked yesterday about notation and things of that nature, so today we're going to talk about what the graphs look like. Easiest thing to do is just talk about the library of functions. Okay, this is going to be a very useful tool, so make sure you keep this in your handout. If you draw this as we go, then that's even better. Later on in this section, we're going to talk about all the functions we're going to talk about now, and how to transform them into the functions that we are given during our problems in this course, or throughout the course in Calculus 1, Calculus 2 and 3. So it's very important that you're familiar with these, what we're calling the library of functions. It's the basic functions that we use throughout algebra, right? So the first is x. Okay, here I'm using positive x. We'll talk about how to look at negative x, and how that negative kind of transforms our graphs later, right? So the basic form of a linear function is really just x, okay? If I have mx plus b, I'm actually applying some transformations to the basic graph of x, right? So all the stuff we learned in chapter 1.10, I think was, with the equations of lines, was really just manipulations of the most basic form of a line, which is f of x equals x, okay? The next is the x squared function. This is our standard quadratic, okay? The x cubed function is very important. Later on in chapter 3, we will keep going up and up and up and up in powers and see what those kind of look like. But for right now, these three are our most basic polynomials, okay? First degree, second, and third degree polynomials. Okay, next is the reciprocal function, 1 over x. So we saw this graph in the last video. These three are probably like the three most basic. These are really the two most basic. This comes up sometimes. This comes up sometimes. But if you think about it, whenever we have a rational expression or rational function, it's really just manipulations of this function 1 over x. So really, these three are very important, okay? After that, I have 1 over x squared. Basically, it's the same thing as 1 over x, except for everything's positive, right? Because squares are always positive. So it's really just pulling this one up to the positive world, no negatives, when we have 1 over x squared. Next is 2 to the x. This is just really a basic form of an exponential function. Then we have logarithm, which is, as we'll see later, they're inverses of each other. Not necessarily these two, but logarithms and exponential functions are inverses. So these are our basic functions. And then the square root function, which is the inverse of the square function. And then the last one is the absolute value function. Okay, so this is an important function as well. Talked quite a bit about absolute values. We've talked about them in equations and inequalities, but its graph is very important as well, right? We've also talked about absolute value in terms of distance away from 0. Okay, so let's talk about the vertical line test. So in the last video, we talked about when something is a function or not. Basically, if I have an input that has more than one output, it can't be a function, right? So we'll talk about how to verify that graphically, because remember, everything we can do algebraically, we can look at a graph and tell the same sort of information most of the time, right? So if there's any vertical line that intersects our graph at more than one point, then that graph does not represent a function. So vertical line means strictly up and down. There should be no slant, no slope to it at all, right? So here's an example. Here's some crazy little function that I drew. Okay, it should be very clear that this is not a function, because if I draw a vertical line in several places, it will intersect my graph in more than once, right? So this random vertical line I drew intersects my graph in 2 separate places. That means that whatever this input is, it has an output of this and an output of this value down here. So remember what I talked about with our remote control. If I press the up volume button, it should turn up my volume up. If I press it a second time, it should turn the volume up. It should not change the channel, right? I would think that my TV or my remote control is broken. So when I plug in a single value into a function, I should always get the same value out. If I have 2 different options to come out from my single input, it's not a function anymore, okay? So, how to read a graph? We still use points, okay? X, Y to identify points on my graph before it was points on my the graph of my equation, right? It's the same thing, remember, it's just now we're calling it a function instead. So in order to find points on my graph, I use xy, okay? But since I've changed my name from y to f of x, I don't call it xy anymore. I prefer to think of it as x and f of x, okay? Because again, remember, the f of x notation allows me to talk about what I'm plugging in, but when I'm looking at this as numbers, it's still the same sort of deal, okay? So let's say that this is my graph, okay? If I move over from 0 a distance of a, so a becomes my input, and I plug in a to my function, I go to the value of a, and I go up on a until I reach my function. And the value, the output value, the y value that I reach, okay, is my f of a. So I can draw a horizontal line from the intersection point of a up to my graph, and then over to my y-intercept, right, my y-axis, and that'll be the value of f of a. So remember, my points are x and f of x. So if I plug in a to my function, I get out whatever my function is at a, right? So that means that my point is an input of a and an output of what happens when I plug in a to my function. So this point is a f of a, so I go to a, and the output is f of a. Piecewise functions. So we talked about piecewise functions in the last video. I did not graph any for you because we're going to talk about graphs here, right? So now let's talk about a piecewise function. I'll give you an example and we will graph one, right? So I already told you in the last video how piecewise functions work. So now let's graph piecewise functions. So remember, piecewise functions are graphed in pieces, right? They're defined in pieces. From this value of x to this value of x, my function does this. And then from this value of x to this value of x, my function does that, right? And I can have as many pieces as I want or as many pieces as I need, okay? So for this piecewise function, let's say that our function is the constant 2 from all negative values up to and including negative 4, okay? Once I move past 4, okay, all the way up to 0 but not including 0, I become the straight line 1/2 x plus 2, okay? And then from 0 included all the way up to 2 included, I take on the value of x squared. From 2 forward, but not including 2, I take on this exponential function. So if you can see, we're taking on several things. We're taking on a constant function, we're taking on a linear function, a quadratic function, and an exponential function, right? So when I do this, I graph them one at a time. I don't try to graph all 4 of these and just say, oh, I'm done. Because remember, if a graph of a function, if you give me a graph, a piecewise function of a graph, and I can draw a vertical line through it, and I hit more than one function because you decided to graph all of the functions all at once and then erase the overlap portions of it, that's no longer a function, right? So you have to make sure that you're only drawing what is described, okay, where it's described. All right. So we have our graph here. So from negative infinity up to negative 4, so from here all the way up to negative 4, we have a constant value of 2. Okay. Now if you look at this endpoint, negative 4 includes the value of 2. So when I look at this function, if I were to plug in negative 4, this is where I would look. I would get out a value of 2, not the value here. Okay, so I'll put a closed dot there. Now from negative 4 to 0, so from here to here, I have the value of 1/2 x plus 2. Now there's 2 ways for you guys to do this. Okay, you can graph 1/2 x plus 2. So you start at 2 and you go up 2 over 1, up 2 over 1, and so forth. Or I guess, I'm sorry, I'm going this way, right? So I start at 2 and I would go down 2 over 1, down 2 over 1, down 2 over 1, and then do the same thing in this direction, but only, and I can do that for the whole graph. Let's just say I do it for the whole graph. However, once I get to where I am already defined, so up until negative 4, so again, let's say I'm here, and I go down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. And I continue to do that. Once I get past this function, I either need to stop or I can continue to keep going, but I erase the function that doesn't belong over that interval. Okay, so that's one way to do it. Okay, so here I have my function 2, and I go down 1 over 2. I was doing it wrong. I go down 1 over 2, down 1 over 2, right? This is my run and this is my rise. So this is the line that I would have because it's from -4 to 0. And then now I look at my endpoints. -4 is not included, neither is 0. So I should put open circles on the ends of both of these. Okay, so that tells me if I'm looking graphically, if I'm looking at this, I know that -4 does not belong to this line, but -4 gets evaluated here where the closed dot is. Okay, I'm going to do the same thing here. I have just a standard x squared function. I could draw the whole thing and erase anything that's not from 0 to 2. Okay, however, this is just a standard x squared. It's very easy to draw just half of that, right? So I really only have to draw the 0, 0, the 1, 1, and the 2, 4, because those are the only parts that are of interest. Those will all get closed dots because 0 and 2 are included as endpoints at this point. Okay. Oops. And then here I have my exponential function. Okay, if you're familiar with the way exponential functions work, you can use it. Just go ahead and plot it. Or perhaps you're not and you need to actually plug in values, so you can plug in 3, plug in 4, plug in 5, and get your output values here. But it will look like this. Okay, I don't have to go any further than that because my graph only exists from basically -6 up to 6. Okay, so I just need enough to fill up my graph. So this is my piecewise function. Over this interval, I have one thing defined. Over this interval, I have something else defined. Over this interval, I have something defined. And over this interval, something else that's defined. Right? And that's how we graph a piecewise function. That's how we evaluate a piecewise function algebraically. We just make sure our inputs are being evaluated at the proper place. Okay? See you guys in the next video.